Okay, so imagine this for a moment. The universe is not quiet. It's filled with radiation, violent collisions, unstable stars, drifting debris, and forces powerful enough to erase entire worlds. And yet, somehow, Earth became a place where life survived. Number 10. The protective local bubble. In the vast and chaotic environment of the Milky Way, interstellar space is far from empty or peaceful. It's filled with radiation, cosmic rays, and streams of energetic particles that, in large enough amounts, can affect planetary environments in significant ways. And yet, here we are. Our solar system travels through this galaxy under conditions that, from a broader perspective, appear surprisingly favorable, as if, within all the chaos, there are small regions that are comparatively calmer than others. In 2022, using data from the Gaia spacecraft, astronomers confirmed that our solar system currently sits inside one of these regions, a gigantic cavity roughly 1,000 light years across known as the local bubble. It isn't a perfect vacuum. Instead, it's a region shaped millions of years ago by multiple supernova explosions, dying stars that blasted away much of the dense material surrounding them. Imagine that process for a moment. Stars collapsing, releasing unimaginable amounts of energy, and eventually leaving behind a thinner, more diffuse region inside the galaxy, a different kind of environment. What makes this especially interesting isn't just the bubble itself, but when our solar system appears to have entered it. Current models suggest that happened around 5 million years ago, and while no direct causal connection has been confirmed, the timing overlaps with important shifts in Earth's climate and with key stages in early human evolution. That does not prove a relationship. But it is the kind of coincidence scientists continue to investigate carefully. Because if the universe teaches us anything, it's that small environmental changes can produce enormous long term consequences. Today, we inhabit a region of the galaxy that appears, at least in some respects, more stable than others. Not as the result of a miracle, but as part of a long chain of astrophysical events that somehow ended up intersecting with our own existence. Number 9. The gravitational bodyguard. When we look at Jupiter, we see a violent giant covered in endless storms, a distant world that feels completely disconnected from life on Earth. But its role in our history may be larger than it first appears. With a mass more than 300 times greater than Earth's, Jupiter dominates much of the solar system gravitationally. Its influence extends far beyond its orbit, constantly interacting with comets, asteroids, and wandering debris. For decades, scientists proposed that Jupiter may partially act like a gravitational shield, deflecting or capturing some of the material that might otherwise move toward the inner solar system. Today, researchers think the picture is more complicated. In some cases, Jupiter may also redirect objects inward rather than protecting us from them. But one thing is clear, its influence on the architecture of the solar system is enormous. Space is not empty, it's filled with fragments, unstable trajectories, and silent collisions happening over millions of years. And in the middle of all that movement, Jupiter acts as one of the system's major gravitational players. A dramatic example occurred in 1994 when comet Shoemaker-Levy 9 was captured by Jupiter's gravity. Instead of continuing deeper into the solar system, the comet broke apart and collided directly with the planet, leaving visible scars across its atmosphere. Events like this remind us that gravitational interactions are not abstract ideas, they are happening constantly. And when astronomers study other star systems, the story becomes even more interesting. Many giant planets, especially so-called hot Jupiters, appear to migrate inward toward their stars, disrupting or even destroying rocky planets in the process. Our Jupiter seems to have followed a different path. Some models, like the Grand Tack hypothesis, suggest Jupiter migrated inward early in the solar system's history before reversing direction due to Saturn's influence. That movement may have helped shape the relatively stable planetary arrangement we see today. Not a perfect system, not fully understood, but one of many processes that eventually created the environment we now live in. Because in the end, Jupiter is not a conscious protector. It's simply another example of how, within enormous indifferent forces, certain configurations can accidentally create conditions where stability becomes possible. Number 8. The impossible moon. Look up at the night sky. There it is, silent, constant, the moon. At first glance, it feels ordinary. But the more closely scientists study it, the stranger it starts to seem. Compared to most planetary systems, our moon is unusually large relative to Earth. Its diameter is more than one quarter that of our planet, a proportion that is surprisingly uncommon. For decades, researchers searched for an explanation. Today, the leading model is known as the giant impact hypothesis. Around 4.5 billion years ago, a Mars sized object likely collided with the young Earth. The impact was catastrophic. Material from both bodies was blasted into orbit, eventually merging to form the moon. Not a perfect process, but one of those rare cosmic events capable of permanently reshaping a planet, and its consequences are still affecting Earth today. Without the moon, Earth's axial tilt might vary much more dramatically over long periods of time, similar to what may have happened on Mars. Instead, the moon helps stabilize that tilt, keeping Earth's climate relatively consistent across geological timescales. That stability affects the seasons, the climate, and the continuity of ecosystems. Its gravity also drives the tides, creating constant motion in Earth's oceans. Some researchers suggest those tidal environments may have played an important role in early prebiotic chemistry. It's strange to think about it this way. A violent collision billions of years ago eventually produced a quiet companion that still shapes life on Earth every single day. The moon is not impossible, but it may be one of those unusually fortunate pieces that, once in place, helped everything else work a little better. Number 7. The rock thermostat. If you look at a world map, something immediately stands out. The continents almost appear to fit together like pieces of an ancient puzzle. That isn't an illusion. It's evidence of plate tectonics, one of the most important and possibly rare planetary processes we know of. As far as current evidence suggests, Earth is the only known planet with a crust divided into moving plates, drifting slowly across a dynamic interior. Nearby planets like Mars and Venus do not seem to operate this way. Their surfaces are comparatively rigid and inactive. And this changes everything, because plate tectonics does far more than create mountains or earthquakes. It also helps regulate Earth's long-term climate. Through what scientists call the carbon silicate cycle, the planet slowly recycles carbon between the atmosphere, oceans, crust, and mantle. Volcanoes release carbon dioxide into the atmosphere, helping trap heat. Rain and chemical weathering gradually remove some of that carbon and lock it into rocks and ocean sediments. Over millions of years, tectonic activity carries portions of that material back into Earth's interior through subduction until volcanic activity releases it again. A continuous cycle, slow, persistent, almost like a planetary thermostat. When Earth warms, weathering tends to increase, removing more carbon dioxide and gradually cooling the climate. When the planet cools, the opposite can happen. Not a perfect balance, but stable enough to maintain liquid water for billions of years. And that may be one of the key reasons life endured here for so long. Without this process, Earth's history could have looked very different. Venus may have experienced a runaway greenhouse effect. Mars gradually lost much of its internal activity and atmosphere. Earth followed another path, one where the planet's interior remained active, where the surface kept changing, and where that movement helped preserve a delicate long-term balance. Not perfect stability, but enough stability for life to persist. Number 6. The radioactive core dynamo. Deep beneath your feet, thousands of kilometers below the surface, something invisible is happening right now. A vast ocean of molten metal, iron and nickel moving slowly through Earth's outer core, generating enormous electrical currents. This process is called the geodynamo, and it creates Earth's magnetic field, an invisible shield surrounding the planet. But what makes it remarkable is not just that it exists, it's that it has remained active for billions of years. For the geodynamo to continue functioning, Earth's core must stay hot enough to remain partially liquid and in motion. And one of the key reasons that happens may involve radioactive elements buried deep within the planet: uranium, thorium, and potassium 40. As these elements decay, they release heat gradually over immense periods of time. Not violently, not suddenly, slowly, continuously. That heat helps maintain the internal motion sustaining Earth's magnetic field. And the magnetic field changes the entire surface environment of the planet. The sun constantly emits charged particles known as the solar wind. Without magnetic protection, those particles can gradually strip away a planet's atmosphere. Mars likely experienced something similar after losing much of its magnetic field billions of years ago. Earth, meanwhile, retained its shield. Not perfectly, not permanently unchanged, but well enough to preserve an atmosphere capable of supporting oceans and complex life. It's strange to realize that processes occurring in total darkness, deep beneath the surface, may ultimately shape every breath we take. Not a flawless system, but an extraordinarily delicate balance that has managed to survive across geological time. Number 5, the balanced water anomaly. Everyone knows water is essential for life, but what often gets overlooked is this. It's not just the presence of water that matters, it's the amount. Earth is called the blue planet, yet compared to its total mass, the amount of water here is actually surprisingly small. A thin outer layer spread across the surface, and slight differences in that balance could have created completely different worlds. With much more water, Earth may have become an ocean planet with little or no exposed land. With far less water, it may have resembled a dry, hostile desert world. Instead, Earth sits somewhere in between. Enough water to sustain global oceans, and enough exposed land to create a wide diversity of environments. The origin of Earth's water is still debated. Some likely existed during planetary formation. Additional amounts may have arrived later through water-rich asteroids and icy material from farther out in the solar system. Not a perfect delivery, but the result of multiple overlapping processes. Today, that balance influences nearly everything: climate, geology, ecosystems, and the possibility of complex life itself. Earth is neither completely flooded nor completely barren. It exists in a narrow middle ground, and in that fragile balance, life found room to evolve. Number 4, the strangely peaceful star. When we look at the sun, it feels stable, predictable, almost ordinary. But on a galactic scale, that impression becomes less obvious. The sun is a G-type star, a category that represents only a fraction of the stars in the Milky Way. Most stars are smaller red dwarfs. For a long time, scientists assumed red dwarfs might be ideal places to search for life because they are extremely long-lived. But detailed observations revealed a problem. Many red dwarfs are highly active, producing intense stellar flares capable of blasting nearby planets with radiation. Our sun, by comparison, appears relatively calm, not perfectly quiet. It still has cycles and solar storms, but over long periods, its energy output has remained comparatively stable, and that stability may have mattered enormously. For billions of years, sunlight reaching Earth stayed within ranges compatible with liquid water, long enough for life to evolve step by step. But there's another strange detail. Early in its history, the sun was significantly dimmer than it is today, roughly 70% of its current brightness. By simple calculations, Earth should have been frozen solid, and yet geological evidence shows liquid water already existed. This is known as the faint young sun paradox. The most widely accepted explanation involves Earth's early atmosphere, which likely contained stronger greenhouse gases capable of trapping additional heat. As the sun gradually brightened over time, Earth's atmosphere also changed. Processes like photosynthesis and carbon cycling altered atmospheric composition, helping regulate planetary temperatures, not a conscious adjustment, but a complex interaction between star, planet, and life evolving together over billions of years. The result is the world we know today, a place where sunlight is neither too intense nor too weak, and where, within that moving balance, life managed to survive. Number 3, the surprisingly stable orbit. Physics tells us planets do not travel in perfect circles, they move in ellipses. And when astronomers began discovering exoplanets, they found that many planetary orbits are far more eccentric than Earth's. Some worlds swing extremely close to their stars before moving far away again, creating dramatic temperature extremes. Earth's orbit, by comparison, is unusually moderate, not perfectly circular, but close enough that the amount of solar energy reaching the planet remains relatively stable throughout the year. And even small differences can matter. A significantly more eccentric orbit could produce far harsher seasonal variations, and more unstable climate conditions. Not necessarily impossible for life, but very different. And there's another layer to this. Earth's orbital stability does not depend only on Earth itself, it depends on the gravitational balance of the entire solar system. Every planet influences every other planet in a long term gravitational dance. Simulations show these systems can be surprisingly sensitive. Small changes in mass or position can alter orbital behavior over millions of years. Yet, our solar system has remained relatively stable for an extraordinarily long time. Not rigid, not permanent, but dynamically balanced. A cosmic choreography where each object influences the rest. And within that balance, Earth remained inside a range where liquid water could persist on the surface. Not guaranteed forever, but stable enough for life to continue evolving. Number two, the seemingly synchronized extinctions. Mass extinctions are often imagined as meaningless catastrophes, moments when life nearly disappeared forever. And in many ways, they were. But when scientists examine the fossil record over vast timescales, something more complicated emerges. These events did not end life, they redirected it. 66 million years ago, an asteroid roughly 10 kilometers wide struck Earth near what is now the Yucatan Peninsula. The impact altered the global climate, darkened the skies, and contributed to the extinction of around 75% of species, including the non avian dinosaurs. For over 160 million years, dinosaurs dominated Earth's ecosystems. Meanwhile, mammals occupied relatively small ecological niches. After the impact, that balance collapsed, and new evolutionary opportunities appeared. Not a planned reset, but a radical change in planetary conditions. Without that event, evolutionary history may have unfolded very differently. And it was not the only turning point. Around 252 million years ago, the Permian Triassic extinction devastated marine and terrestrial life, likely connected to massive volcanic activity. Long before that, rising oxygen levels transformed Earth's biosphere, eliminating organisms unable to survive in the new environment. Each event was catastrophic, but each also reshaped the evolutionary landscape, not evidence of purpose, not evidence of design, just a reminder that life evolves in response to a planet that keeps changing. And within that constant tension between stability and crisis, complexity eventually emerged, including us. Number one, the anthropic principle. After all of this, all these delicate balances, all these unlikely conditions, one question becomes unavoidable. Why does any of it work at all? In physics, there is an idea known as the anthropic principle. At its simplest, it says this: we observe a universe compatible with life because if it were not compatible with life, we would not be here to observe it. It's not necessarily an explanation, more like a starting point, but the deeper scientists explore this idea, the stranger it becomes. Because it's not only Earth that appears finely balanced, it's the laws of the universe themselves. Tiny variations in certain fundamental constants could have produced a radically different cosmos. If the forces holding atoms together were slightly different, elements like carbon and oxygen might never have formed. If gravity were significantly stronger or weaker, stars, galaxies, and planets could behave in completely different ways. Small changes, enormous consequences, and this is where science reaches the edge of interpretation. Some researchers explore multiverse models where countless universes may exist with different physical conditions, and we simply happen to live in one compatible with life. Others suspect deeper physical principles may eventually explain why these constants have the values they do, and some interpretations move into philosophical territory entirely. Right now, there is no final answer. What we do know is this: we live in a universe where matter was able to organize, where stars formed, where planets evolved, and where, eventually, conscious beings emerged capable of asking where they came from. Not necessarily because the universe was designed for us, but because among all the possibilities, this is one where observers can exist, and that alone is extraordinary. Because beyond every equation and every theory, the fact that the universe became aware enough to look back at itself may still be one of the strangest things we know. The Earth is not perfect, the universe is not simple, but somewhere in the middle of all that complexity, a fragile balance emerged, one that allowed matter to become conscious of itself. And maybe that's the most fascinating part of all. And remember, the universe doesn't reveal its secrets to those who rush. It reveals them to those who know how to look. Subscribe and keep listening to the silence.